Okay.
Recording very fast.
I am. I'm going to see if that works.
It should.
Abby was going to try too, and we'll just get both going. But it looks like it actually works pretty well that I can get both the whiteboard and this in the frame and me when I'm standing here.
Yeah, it might be even better that way. The volume is always good too.
Yeah. All right, so let's start talking a little bit while everybody is coming in about questions on the plans and stuff. So I sent a bunch of things out to you guys about, so I gave everybody feedback on their plans. Does that make sense to everyone what I said? And I think the key at this stage and for this paper is to keep things short and sweet. Ask a couple of questions that you're sure you're going to be able to do in the time allotted, and then see where you are. As opposed to trying to take on a big idea or a really complicated thing, you can have those in your brain, and you can use those in the introduction of the paper to motivate what you're going to do, but then the actual results you're focusing on can be a lot smaller in scope. And that's true of scientific papers in general. When you write them, you write this introduction that's like, these are the most important ideas of all time. And then you say, and so I'm going to look at this one little piece of it. That's what I have access to today with the data I've collected this week or whatever. And so that scoping is always true. In this case, it's sort of more imperatively true because the time scale for how much time we have to work on these papers is very contracted. But that practice of getting used to big questions, small results, is actually part of how science works in general. So this is just an example of that. Does that make sense to everybody? So the two classes of things are budget-related things. We're going to talk about budgets today. So your budget-related things might be very much like what we're going to talk about today, or statistics-related things. And essentially the closest statistics-related thing is the bootstrapping stuff that we did on the homework. And so we didn't talk much about how bootstrapping works. But basically the idea is you're resampling a set of data to put an uncertainty on some summary statistic of that data. So if I have 10, say I have 10 data, and I want to know how uncertain their average is. Well, I can make the average out of those 10 data, but that doesn't tell me anything about the uncertainty in the average. But I could make another set of 10 data which looks an awful lot like that by choosing 10 random values out of those 10 data. And the key that makes bootstrapping special is that you allow yourself to repeat them. So I might pick number 1 twice, and then 2, 3, 4, 5, 6, 7, 8, and then I'm done. So that's not the same as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, because I picked one of them twice. So if I take the average over that set, it'll be a little different because one of the data has been left out and one has been doubled up. Does that make sense to everybody? How that works? So it's like you take the data and then you draw out of it the same number, but you allow yourself to repeat if you need to as you're drawing out. So you get a little bit different data set every time you do that. And if you do that over and over and over and over and over again, it turns out that the distribution of those sampling with repeats actually gives you a pretty decent estimate of the uncertainty in the original average. So every time you draw a sample, you get a new average that's a little different. And if you keep doing that over and over again, you get a collection of averages. And the uncertainty in that you can prove has something to do with the uncertainty in the original average over the data you had. You can also do it with the variance. You could do it with more complicated things that you were constructing out of that. Not all of them are provably the same, but that's the idea of bootstrapping. And so bootstrapping is one way you can use a data set to explore its own uncertainty. You can also use theory, like the square root of n number of observations. As you collect more observations, the uncertainty goes down. So if you've taken a statistics class, that might make sense. Or you can do another thing that's closely related to bootstrapping that's called jackknifing, which is where you just throw some of the data out. So if I had 10 data points, I could eliminate the first one and see what the average is. I could eliminate the second one, see what the average is. I could eliminate the third one, and you can subsample like that. That one, is a little more limited because there are not very many ways to exclude data. So you don't actually get a lot of different samples out of that. So it doesn't have as good of statistics as the bootstrapping, because there are lots and lots of ways to choose 10 data points out of 10 if you allow yourself to repeat. Take 10 data, exclude one, there are only 10 ways to do it. You can exclude exactly one of them, each of them once, right? So does that make some sense to people? So that's the statistics side of stuff. So essentially you could take any location you want, take any collection of data you want, and just start thinking about how those things relate to like the mean temperature or the mean salinity in this region, or something like that. The budget side is what we're going to talk about today, and that's a little bit more specific to using a model or using a particular location where you happen to have data on all of the edges of the location. So we're going to talk about one example, which is an estuary first. So does everybody know what an estuary is? Narragansett Bay is an example. It's a body of water that's closed on one end, or it's closed all around, and then it has an outlet to the ocean, and then rivers and rainfall feeding it. So what do you think would happen? What happens if you rain on Narragansett Bay? Yeah.
It will become less saline.
It'll become less saline, and there'll be extra water in it. So maybe if it was just raining inside the bay, some of that water would have to run out to keep the sea level the same between the ocean. Or a different way to think of it is, as the tides come and go in the ocean, so the ocean level is going up and down, the water is rushing in and out of the bay. So we have these exchanges with the ocean, and also sources of fresh water, like the rivers and rainfall, and then sinks of fresh water, like evaporation in the bay. So we're going to use our equations that we discussed last time, the conservation of mass, to start thinking about how that works in an estuary case. Okay? And we're actually also going to use the conservation of salinity, or the conservation of salt. And that turns out that that's enough to do an awful lot of things with, from just in that particular case, because the volume of interest, the control volume in the language we used last time, is specific. And so when you have a control volume, you can use all of these integral relationships, like the divergence theorem, to really convert from the things you know into the things you don't know but would like to know, and back and forth. So that's the way this proceeds. Does that sort of sound reasonable? It's going to get a lot more specific, and that helps, because this is kind of the easiest to grasp version of this that makes sense. Okay, so here's our material derivative we spent a lot of time thinking about last time. So this is the material derivative of density. What does this tell us?
How is density changing over time in a particular packet of water?
Right, as we follow the packet of water, does the density go up or down? That's what this term tells us. And this one is the divergence. Remember, and we talked about flow coming into a point would have a negative divergence, flow going out of a point to have a positive divergence, times the density. But if the density is constant, what's this? 0, because it's got either a space derivative or a time derivative in the two terms that make this up. And both of them would be 0 if the density was the same everywhere. And if the density is the same and non-zero here, we could divide through, and then we just have this left over. The divergence of the velocity is equal to 0. So this is called incompressibility, and you can think of that two different ways. When it's not diverging or converging, you're not compressing. You don't converge it to a point, you don't diverge from a point. Or you can think, if it was getting compressed, the density would have to go up. The density is not changing, so it's not compressing, it's not expanding, density is constant. So incompressibility, either way you think of it, this is equals 0 or this equals 0, they're both talking about the same thing from the perspective of the conservation of mass. So that sort of makes sense to everybody? The ocean is actually not incompressible. There are changes in salinity and temperature and pressure enough that the density changes by about 3%. So it is approximately true that this is close to zero. That is, this term is a lot smaller than this guy doesn't play as big of a role in this equation as setting that approximately equal to zero would be, but it is at the same time true that this isn't quite zero. This is a little bit different from zero. So that's a weird limit to be in, but we can frequently just assume that the ocean is approximately incompressible and proceed on, and that's what we're going to do in the estuaries. Next time we're going to talk a little bit about the compression of seawater, particularly if you take a partial at the surface and jam it down to the bottom, because its temperature changes as it gets compressed. And so there's some thermodynamics we want to have in mind. We'll walk through that next time. There's some consequences about the way we handle temperature that are careful. But most of the time we can forget about that and just say, this is what we mean by conservation of volume, and conservation of volume is approximately the same as conservation of mass because the density doesn't change very much, even though it changes a little. Is everybody okay on that front? All right. So we can talk about being incompressible and the conservation of volume, and here's our imaginary estuary. So this is like down near Newport. We have a sill, and there's the ocean over there, and this is up where we are. Providence River, Seekonk River are coming in, so we have a river inflow. We have an exchange flow, possibly, so something's flowing out, something's flowing in. We don't know whether the outflow is down at the bottom or at the top. We just know that there's an out and there's an in. What would be the difference between being at the bottom and being at the top? When would it tend to flow out at the top?
More fresh water.
If it was fresher or less dense.
Yeah.
So if we had fresher, warmer water, it would tend to flow out on the top. If, on the other hand, once we think about all this stuff, if what the bay does is it actually produces saltier water, that is, if evaporation dominates over precipitation in rivers, it might flow out at the bottom. And we'll have two examples of that, one in each case, for different real-world estuaries that we'll see in a minute. Okay? But anyway, this is for notational purposes. There's an out, there's an in. There's precipitation, there's evaporation. Those are both in units of meters per year or whatever. It's really a velocity. It's the velocity at which fresh water is going out or coming in. And then there's an area. And then we might take this in terms of a cubic flow, so meters cubed per second, or it might be a cross-sectional area of the river times the velocity, the same way that we were thinking of just a second ago with evaporation and precipitation. Okay, so how do we use that equation in this setup? Yeah?
Precipitation plus river flow plus flow from the ocean and has to equal the evaporation that will flow out.
Right, so you're thinking, you've already converted from the fact that this was stuff going into a point, stuff going out, that all the inflows have to equal the outflows. We can't compress, we're incompressible, so we don't get extra stuff piling up, we don't get extra stuff going out. There's a little bit of a subtle point in that requires that the sea level is not rising. Like, we could change the volume of this and have a little imbalance for a while, but if we're not changing the volume, then we would expect those inflows to balance the outflows. We can actually do it directly with calculus by saying we just take del dot V equals 0 and integrate over a volume. What volume? The volume of the estuary. Okay? So integrating del dot V over the volume of the estuary, and since del dot V equals 0, the integral of 0 is also 0, so that part is the same. And then here is the divergence theorem going from there to there. So what does this tell you? This is the velocity dotted into a normal in the surface direction. And this is now a surface integral, not a volume integral. So what is this? What does that tell you? What are some examples of the terms in this? Exactly. So del.v is evaluated everywhere inside, but the divergence theorem tells us that we can integrate that over the whole volume and just treat the surfaces coming in and out. So this one says, take all the surface flows, and they have to add up to 0. And the little circle on the integral means you have to consider every single interface. You can't forget one, because that might be an inflow or outflow there. Okay? Yeah?
What about everything on an interior being density that's combined of salt and water versus like the river and precipitation, which is only water?
Absolutely. Super confusing, but we got to this incompressibility by saying that the density doesn't change very much, or in fact that the density is constant to have strict incompressibility. So we're assuming that variation between seawater density, so say 4%, 3% above 1,000 kilos per cubic meter versus freshwater density, which is 1,000, actually 1,000, that difference is small, which means that 0 approximately is del.v, which means that this is a budget just for the volume of freshwater. We're not talking about salt or temperature or mass even, we're just thinking of volume at this stage. So in a second we're gonna add salinity in, and that'll be a separate constraint. So we'll have the freshwater constraint and the salinity constraint. We put those two together and we'll get more interesting results. Okay, so here's this. Now I just expand it out. Here's the one through the inflow area. Here's the outflow area. Here's the precipitation area. Here's the evaporation area. Here's the river area. Or we can just give those all a letter that says the volume of inflow. And what are the units of that? Meters per second. This is a velocity times area. So meters cubed per second. Meters cubed per second flowing out. Area of the surface times the precipitation in meters per second. So this is a volume, the product is a volume. Evaporation times the area of the surface, and the river inflow. So that budget, VI plus V minus VO plus blah blah, that says we're not gaining any stuff any more than we're losing. We're just in balance. And the signs here are following the direction of the arrows. So there are some funny little minuses and pluses, but I think everybody can figure out how that all works, right? Okay, yeah.
A quite unrelated question. I'm just curious, how does the sill form?
How does the sill work?
Yeah.
So the sill is really just a place where we've decided to measure.
Right.
We could have measured anywhere else, but frequently the way that an estuary works is that the sill is easier to measure. It's kind of a smaller region.
And how does it form?
Oh, how does it form?
Yeah.
Let's see, here it forms because the glaciers that formed it came down and then they dumped at the end. And so this Newport, and so the two big islands, Aquidneck and Connecticut, are like the ends of where the glaciers went. And so there's also a sill underneath. But in other basins, it might be formed in a totally different way. It's not clear that you would have a sill. It could also just be a linear slope all the way out, and you just say, I'm just paying attention to where I've decided to make my measurements. So it's not too specific that you don't have to have a sill to have an estuary. But frequently estuaries have them because they're formed with a process like glaciers that have put a pile at the end and then they're deeper a little bit farther in. Does that make sense? Fjords, that kind of thing. Okay. All right, let's think a little bit about the salt conservation part. So the last part was freshwater. Now we're gonna think about salt. So there's a salt budget that looks an awful lot like the mass budget, except it says the rate of change of salinity could be some kind of sources of salinity, which might be mixing. It is a little different in this case. Or it could be that you take sodium and chloride separately, you add them together, and then you get salt. So there could, unlike mass, you could have a source of salt. unlike mass, you could have a source of heat. And so some of our equations aren't going to look like material derivative of something equals 0. They might look like, or material derivative of something, well, sorry, material derivative of something plus convergence part equals 0. They could be a little different. All right, so what happened? What happens to the other part of that equation? So we did d rho dt plus rho divergence del dot v equals 0. And we said this part was equal to 0 approximately. So it turns out that if you're thinking of salt as grams of salt per unit volume or grams of salt per unit mass, you actually get two slightly different equations in a compressible fluid. You get one that looks like that guy, which goes ds dt plus the divergence of velocity times salt equals 0, or equals s dot, or ds dt equals s dot. So this one is if, let's call this one salt twiddle, because these are kind of different. So this is salt measured in a funny way. This is salinity measured in kilograms per cubic meter. And this one is grams per kilogram, or just mass fraction of salt. Okay. These are really, really important differences in the atmosphere where there's convergence and divergence. So humidity in volume fraction and humidity in mass fraction are really different things. But I'm claiming that it doesn't matter which one of these equations I use for salinity, and why is that? It's approximately incompressible. So let's write out what this is. This is ds by dt plus v dot grad s equals s dot. And this one, I could expand that out and write it as ds twiddle by dt plus v dot grad s twiddle plus s times del dot v s twiddle. But if this is almost equal to 0, then this is pretty much the same as that. So as long as it's relatively incompressible, we don't really care which way we write it. We can take it to be this kind of equation, or we can take it to be this kind of equation. They're both, we end up in the same place as long as we're willing to hold on to del dot v is equal to 0. Does that make sense to everybody? So in other fluids that are compressible, strongly compressible, we would have a whole week of lectures figuring out how to think about the mass fraction and the volume fraction. In ocean flows, where we almost always are nearly incompressible, it doesn't really matter which one we have. We can take either equation, we get to the same place in the end. Okay? Does that make sense to everybody? So in this case, it's actually more convenient to take this form than it is to take this form, because this guy's got a divergence of something in it. So if we integrate this equation, we have the rate of change of salinity at a point integrated over the volume, plus the divergence of salinity times the volume, times the velocity, integrated over the volume. Everybody following me how I get from here to there? And this is the same as that. Everybody's following me? This equation, this equation, this equation, just a volume integral of that. Okay? Okay. So if this equals 0, I can just rearrange the things on different sides. What is the partial derivative of salinity with respect to time integrated to the volume? If it's a fixed volume in time, so our control volume of our estuary, and our estuary is not changing depth, I can pull the ddt outside, And then this is just the ddt of the salinity inside the volume, which is approximately equal to the ddt of the density times the salinity, since the density is also not changing with time. And this is basically just the mass of salt inside the bay. So as long as we're not adding salt or taking salt away, we're in steady state. This guy is going to be close to 0. Does that make sense to everybody? What about this part? The volume integral of the divergence of this. What did we do last time when we had a volume integral of the divergence of the velocity? We had the volume integral of the divergence of the velocity. And then we used the divergence theorem to say, oh, that's just the flows in through the side of the velocities through the side. And then we went through them all and we figured out some of them were runoff and some of them were inflow and outflow. So what are they in this case? That means that the divergence of the salinity times the velocity is the thing we want to think about through all of the volumes on the through all the surfaces. Does that make sense to everybody? And if this is approximately equal to 0, then this thing has to be equal to 0 as well, right? So if this is 0 because the sum is 0. Okay, so where do we have to worry about salinity times velocity? On the surfaces, the bounding surfaces of our estuary, which are here. Okay, is there any velocity times salinity coming in this way? No. Why do you say no?
Because it's fresh water.
Because it's fresh water. So there's velocity, but the salinity is 0. Is there any velocity times salinity coming and going this? No, because the rainwater is fresh and evaporation leaves the salt behind. So these fluxes also have 0 salinity. But now there is salinity in this, and the salinity could be different in the outflowing water from the inflowing water. So we just need to take those two contributions, and that's our other little bit of the budget. So the velocity times the salinity of the inflow has to equal the velocity times the salinity of the outflow. Because these are the only two salt sources. And if the mass of salt inside the bay is constant, that's this part, then we just went through the derivation to say that the inflow of salt equals the outflow of salt. So now we've got two different equations. We've got one that says salt coming in equals salt going out, and one that says volume coming in equals volume going out. And they're different because they use different generating equations. So we can put them together and come up with Knudson's relations. So this is the volume out minus the volume in equals the rivers plus the precipitation minus the evaporation, or just the fresh water sources all together. And then the volume times the salinity coming in equals the volume flow going out times the salinity going out. Okay? And all of these volumes are measured in meters cubed per second, and the precipitation and evaporation are a velocity. Okay? But I could eliminate, say, the outgoing velocity between those two equations. I could just, move the SO on this side and cancel that out. And that is this one. Does everybody see how that worked? Or I could have eliminated the inflow volume flux. And then I get this. Okay, so stare at those for a second. And let's remember what our little schematic is. We have the exchange flow at the mouth of the bay. V out, S out, V in, S in. We have the river. We have precipitation. We have evaporation. And the combination P plus R minus E equals the freshwater source. Area. Okay. Let's think about this one first. Okay. We talked about the idea that you probably have flow out if there was river coming in. When does the amount of flow out equal the rainfall minus evaporation plus the river. What has to happen according to this relationship? If I want V naught to be equal to F, what has to happen to this crazy thing?
The salinity out would be 0.
The salinity out would be 0. So then it would be salinity in over salinity in, just 1. So if the river just came out and just slid on top of a saltier bit and didn't do anything, that would be fine. And that would say that V out equals freshwater source. Does that make sense, everybody? What if it's really, really well mixed so that SN equals S out? It explodes. You can't do it. You can't make it that way because you can't balance that amount of outflow with a freshwater source. There would be too much outflow would be required to keep up with that. But you could get close to that. Suppose these are really nearby each other, and then it would just say the outflow is much, much bigger than the freshwater source. Or to put it another way, imagine we have a little river and it starts mixing. As it's mixing, it's grabbing a bigger and bigger hunk of water, and that bigger and bigger hunk of water is flowing out of the bay. It's entraining a lot of salty water on the way out. That's what happens when SN and S out are close to each other. A small amount of fresh water drives a large outflow because of a lot of entrainment through mixing. Does that make sense to people? Some plausible sense? What about the inflow part? When does the inflow equal the freshwater source? Or can it? It sort of can't, right? I mean, you could make it be equal in magnitude if SI minus SO was equal to SO. So SN was as different from S out as S out itself is. So suppose S out has a salinity of 1 and SI has a salinity of 2. Then SI minus SO is 1, and this would be 1 over 1. So if the salinity is half as much flowing out as it is inflowing, then the inflow would equal the freshwater source. And what has to happen on this case? If SI, if that was true, if SI is, then this guy would be 2. So this would have to be 2 times as much. Where does the other one come from? The inflow is 1 unit of F. The outflow is 2 units of F. How's that work? Sorry, you said it, I think. The precipitation. The fresh water is the other unit. So in the case where we have 1 unit of inflow coming from the mouth and 1 unit of inflow coming from the precipitation in the river minus the evaporation, that's when the outflow would be 2 units. And the salinity out would be half of the salinity coming in. Because it would take those parts, it would take the salty water and the fresh water in equal parts, mix them together, and end up with something that has a salinity halfway in between. And you'd have to move the volume twice as fast to get the right amount of salt going out as coming in. Does that make sense to everybody? So those are kind of hypothetical cases. We don't have to go hypothetical. We could apply this to the Mediterranean. We could go totally not hypothetical and take observations of the salinity that's flowing in and the salinity that's flowing out. They're 36.3% parts per thousand versus 37.8 parts per thousand. Both in between 3 and 4% salt by mass. And the fresh water is 0, right? So these are pretty close. So what's your intuition? Are we in the limit where there's a lot of flow through or a small amount of flow through? A lot, right? Because in order, this is a small salinity difference, so there's got to be a lot of overturning to get rid of the extra little bit of fresh water that's being added, or actually in this case it's evaporation that's going out through the surface. So in this case, the Mediterranean is actually producing salty water, so evaporation is exceeding runoff plus precipitation. And so the fresh water is a little bit negative, but you can figure out how much it is by taking, if you go and measure the inflow, you go and measure the outflow, you could say, oh, the difference between those two is the fresh water. Or you could have gone through this relationship and used the salinities and just either this one or that one, and you would have gotten the other two. Does that make sense? So it's sort of, you're getting a constraint on the different pieces of that puzzle. You might not know what this freshwater source is. This is actually a really hard one to measure because you have to go and catch all the rain and figure out how much rain and figure out how fast it's evaporating. Normally this one is unknown, but this might be measurable. This might be hard to measure because it's deep, but if you have the shallow one and you know the two salinities, then you can use the shallow one and the two salinities to figure out the freshwater source. Then you can use the freshwater source, the two salinities to figure the outflow, and you get the rest of the relationships. Yeah?
I'm a little confused by evaporation because on one hand we're saying that the salt and the fresh water are separated in scale and the salt is much smaller than the fresh water.
Yeah.
But on the other hand, you're talking about evaporation, which to me seems like a source of salinity also because you're extracting the H2O and then, but it's still not, so it's enough to drive these changes but not enough to count as an incompressibility
Yeah.
thing.
Yeah. So there's the freshwater budget and there's the salt budget. And so this evaporation affects the freshwater budget, but it doesn't affect the salt budget because salt doesn't go out when you evaporate. It just gets left behind. So the fact that VI out minus VI equals the evaporation, the freshwater sink, that's one way of thinking that the different volumes are equaling up. But these relationships are telling you why these salinities are what they are, why they're close to each other, in order for that all to work. So the point of this is not that this is like deep thinking, and you can go through all kinds of other examples of this. The point of this is that a budget, a control volume, is a really powerful thing. You can take a few ideas, like the conservation of freshwater, the conservation of salt, and build a system that allows you to study parts of the world quantitatively and make predictions about things that you don't observe. Does that make sense to everybody? And these work as well as you would expect them to. I mean, like, the only failing in this actually is that we assume that this is steady. And typically what happens is the salinity actually goes up and down seasonally, and there's like plumes of outflow that have different salinity, and so it's kind of complicated to get a good long time average of these pieces. But aside from that, this works. And so this is one kind of budget over a volume of physical significance. We're going to talk about another kind of budget, which is the one we're going to more frequently think of. But we also could, let's see a different example. What if we go to the Black Sea? So does everybody know where the Black Sea is? All right, so this is the Straits of Gibraltar, which is the sill we were using there. But we can go back to the Bosphorus and use these straits, and then we have the Black Sea as our estuary. So it's an estuary that empties into another estuary, if you like, okay? So this one is different than this one. Let's see how it's different. Oops, that's still the Mediterranean. In this case, the outflow is only 17 parts per thousand salt. And the inflow is 35 parts per thousand salt. So this is almost one of our idealized cases that we thought about. This is about half of that. So if this is half of that, that means that this ratio is about 1, which means that the inflow is pretty much equal to the freshwater source. And the outflow is pretty much equal to double that. Okay, so here's the inflow, 6 times 10 to the third cubic meters per second. Here's the outflow, about double. And the freshwater source, 6.5, so almost the same as the inflow. Okay, so qualitatively, this is a really different bay. It doesn't make the water saltier in the bay, it makes the water fresher. The flow that's flowing out is fresher than the flow that's flowing in. If we go back to the Mediterranean, the flow that's flowing out is saltier than the flow that's flowing in. So the outflow is actually on the bottom, the inflow is on the top. And also, these salinities are really close to each other, which means there's an awful lot of overturning for the amount of freshwater sink, the amount of evaporation. In the Black Sea, the freshwater and the inflow are about the same size. So there's not an awful lot of overturning. Or another way to put it, there's not very much mixing in the Black Sea. The deep water is really, really separate from the shallow water. Only about when this freshwater source from the rivers comes in, it only grabs about just as much, just about doubles its volume through entrainment and mixing before it leaves. Does that make sense? Yeah.
So are you saying the mixing is just due to the salinity differences, or is it also because of the velocity?
So this is part of the question. This is a constraint. This doesn't tell us who's doing what. This just tells us a constraint. This says if we conserve freshwater, we conserve salinity, this must be true. It does not actually tell us why it's true. So you could say, well, that's because there's a small amount of freshwater being added, but small in what units? Well, small compared to the inflow, but that's weird because this is only there because of the salinities. Or you could say there's not much mixing, which makes the salinities really different. But is there not much mixing because the inflows were small compared to the outflows? Like, there's no, it's all circular. This is a diagnostic relationship, not a predictive relationship. So this is one of the downsides of budgets, is you can come up with things that have to be true, but they might not tell you much else. They might not tell you why they're true. So we're gonna first work our way through salinity, freshwater, temperature budgets, which don't really have an explanation for why. They're just kind of keeping track of all the beans. We're just bean counting. Beans coming in, beans going out, beans left in the pot. That's the way we're gonna do it for a while. Then we're going to switch to the momentum equation. And in the momentum equation, we're gonna have different kind of beans. They're vector beans, so they have a direction and magnitude, but they also will tell you why there is a velocity there. And so forces and velocities will change your budgets in a different way. And when we get to the momentum equation, we'll start to have a rationale. So we'll say, this exchange flow is wind driven, or this exchange flow results from the pressure difference that builds up because of freshwater and saltwater. Those will be more deeper meaning, like they are more causality related. When we have both the budgets of salinity and temperature together with the momentum budget that tells us why there's a velocity there. But it's gonna take us a while to get there. First we have to get just the bean counting part together and kind of understand how that works. Does that make sense? And so for today, we're talking about bean counting of salinity or salt and freshwater. Next time we're gonna talk about energy, heat, and then, we'll actually talk a little bit about that today before we're done, I think. And then we're gonna start getting into momentum, and whether the momentum comes from the winds, or whether the momentum comes from the salinity and temperature gradients, or whether the momentum, and whether there's an energy piece, and on we go. So we'll have a lot of explanations. So you might have noticed that the subtitle for this class is Notions for the Motions of the Ocean. So anyway, the notions, the ideas for the motions of the oceans are really kind of explanations of what causes the velocities. The motions of the oceans are the interesting part, but getting to there takes a lot of machinery and the differential equations before we kind of know what an ocean equation looks like. Does that make sense to everybody? Okay. All right, so we did, kind of on that note, we did freshwater and salt. We could have done pollution too. We could have had sources of pollution, like factories on the Black River in Russia, and then it would have come out into the Black Sea, and then it would have come out later into the Mediterranean. And because the Black Sea doesn't have a lot of mixing and doesn't have a lot of dilution, you would expect that the pollution impact would be larger there. But then when you get to the Mediterranean, there's this huge overturning and lots of mixing. The dilution would go very, very fast in the Mediterranean. So it is also true that the Black Sea is more polluted than the Mediterranean, but it's not necessarily because there are more sources of pollution into the Black Sea, even though I think that's also true, but it is because the Black Sea doesn't have much mixing, whereas the Mediterranean has a lot of mixing and dilution because of the way that the salinity budget works out at the Strait of Gibraltar. So the pollution is diluted very quickly once it enters the Mediterranean. Does that make sense? So that's another piece of this. Okay, but let's get to where we want to go. So we did all of that by thinking of a volume integral of a differential equation over our estuary. But I could have done the volume integral over any volume I like a grid cell from a model, for example. So I could take those same differential equations that govern the conservation of mass, conservation of salt, conservation of volume, and integrate them over a grid cell. And then I would convert between the rate of change of stuff inside the box versus the flows in and out of the box. And that's actually the basis of what's called a finite volume discretization of differential equations. There's also finite differences, which is subtly different, and then there are other more obscure ones like spectral and whatever, but the ECHO model that we're going to use is a finite volume model, and for the purposes of just understanding how this stuff works, thinking finite volume is a good way to go. Like, how does a model work? Well, it's got a bunch of little boxes. Each of those little boxes is a control volume, and we're just going to add up all those control volumes to think about what's changing. Okay? So the budget exercise for this is to do exactly that with the ECHO simulation. So the ECHO simulation is conserving volume because it's assumed to be nearly incompressible. And so it has all of the velocities flowing into every grid cell equal the velocities flowing out times the cross-sectional areas. It conserves salt, so all the salt flowing into every box also flows out of that box. It conserves potential temperature, which is closely related to temperature, a little different in a way we're going to describe next time. So that's the equivalent of energy conservation. And then it also conserves momentum. So when we get to the momentum equations, it's a little trickier to keep track of what's going on. But we could do just that same exercise with the model's grid cells, the same way we did with that one. So if you go back to the Forget paper that explains the ECHO model that was listed in the homework 1 as something to look at, here are the differential equations explaining the motion, and they're extremely complicated, but here's a salinity equation. That looks sort of familiar. Here's a potential temperature equation, which looks an awful lot like a salinity equation. There's a partial derivative bit. There's a divergence of something that's salinity times a velocity. Great. And then there's other stuff like diffusion and sources at the surface and complicated other stuff. There's a sea surface height equation, because maybe the volume, it's incompressible, but the sea surface height could rise up if you add extra stuff into one box and don't take it out. So there's that equation. And then there's momentum equation, which we're going to come to later. But you could play exactly the game we just played and say, let's do a volume integral of this over a grid cell. And then this would be ddt of the stuff inside that box. This would be the divergence of that stuff coming in and out the sides of the box. There's this funny S star factor, which allows you to change the dimensions of the box on the fly, which is a little weird, but it really only matters in the surface cell, which might get taller and lower as sea level comes and goes. So that's one little complication that is more complicated than we considered for the estuary case. But otherwise, it's just like that.
Sorry, what do you mean by changing dimensions?
So we said our control volume was fixed in size. But if you added water on the top and didn't take it away, it might just be easier to make your box a little taller to take care of that extra water rather than adding a new box to carry that rainwater, say. So this model is framed in such a way that the grid cell dimension might get a little taller in order to handle extra precipitation or extra mass that's added on top, which is essentially a detail, and they used to not do this in ocean models, but when you get really down to the nitty-gritty of sea level rise, it turns out that you need a little bit of flexibility and a lot of accuracy in how you do that. So we can talk when we get a little bit later some of the choices you could have done, but essentially it's just part of this budget conservation piece that we can keep in mind as we go along. And there's a simple way to take care of it in the variables they give to you. They give you this combination or this combination, so including that extra part built in out of the echo model output. So it's transparent to you. You don't have to worry about it. You just need to add together the right variables. Okay, so if you go into the variable list, there's all these crazy things. So there's eta n, which is the sea surface height. There's SIHF, which is sea ice thickness effective. SIH snow, the thickness of snow on top of the sea ice. The ocean freshwater flux. There's the sea ice atmospheric freshwater. There's OCE freshwater flux. There's velocities in different directions. So there's a lot of crazy stuff. I've already given you an example of one of those budgets, and as we work with this model, these acronyms will start to make more sense. But here is what the divergence of E looks like. There's an advection in the east direction, an advection in the north direction, and then on the back side, there's an advection in the north direction into the next grid cell. So these are offset by one index. These are offset by one index. There's an advection through the top, which is offset by one index, and then there's whatever's inside the volume. Does that make sense? So this is one way of doing it. In the particular case of the surface, things get complicated because you have like sea ice melting and turning into seawater, and you have snow, and you have precipitation, and you have lots of complicated bits and pieces to keep track of. But for budgets, especially the ones away from the surface, it's pretty easy just to figure out what the variables coming and going in that particular variable are coming in and out of the sides of the box. And you might have advection that is carried by velocities, or you might have diffusion, like salt might diffuse into and out of your box. And so you would have diffusion parts and advective parts. And each of them has a little E for east, or a little N for the north direction, or a little R for the vertical coordinate. Okay? So there's a lot of stuff here. You should come back to these figures and look at them later if you want to do one of these budgets.
How does this side also have the snow?
So this is the diffusion of snow sitting on top of the ice. So not the velocity, but like the spreading out of ice flows. If they were all concentrated in one box, they would kind of diffuse out of the neighboring boxes, and if there was snow on top of them, it would take it with them. So yeah, it's a little hard to figure out what the physical pieces are always for these, but slowly moving along. Does that make sense, everybody? And so here are all the ones that are involved in the salt and freshwater budgets. So there's diffusions of salt, there's advections of salt, there's diffusions of thickness, there's diffusions of snow, and so you can take all of those together and you should be able to close that budget for any box you want. Okay? But maybe I don't want to do one box. Oops. Maybe I want to do two boxes. Is that fundamentally different? No, because if I put two boxes next to each other, sorry, where is this? If I put two boxes next to each other, the advection out of this box would be the advection into this box. And the diffusion out of this box would be the diffusion into this box. So it would cancel out. So I could just squish them together and pay attention to only the outside boxes. And that's really the same thing as the divergence theorem. This is the discrete analog of the divergence theorem. You take adjacent volume budgets and you hook them together where all the exchanges inside don't leave, and they all cancel out. So you only ever have to pay attention to the outer surface of whatever volume you're paying attention to. And that's why the divergence theorem works. Yeah.
So say you were just calculating how much salinity was coming in from the bottom of just one of the grid cells.
Yeah.
You would take the velocity measurements and the salinity measurements from the grid cell below it and then multiply that by the area.
Yes. You could calculate it that way yourself, each of those pieces, or you could take one of these pre-calculated, complicated things that's already doing those multiplications for you and has it in units of volume flow times salinity or whatever.
Okay.
So there are some subtleties because if these are varying in time and you have the mean temperature or the mean salinity and the mean velocity, the product of the two means is not equal to the mean of the products. So you can lose temporal variability by forming it a piece at a time. So having the combination already done for you helps avoid that issue.
So is the ADVR, is that just the velocity?
This is the advection of something.
Okay.
So depending on which one it is, so in this case, this is the advection in the y direction of salt.
So that has everything included and you just have to multiply by the area?
Yeah, or you don't even have to multiply the area, it already has the area. So this is in units of, I think, salt per unit time, or so it already has the salt delivery into the box. So all of these pieces have metadata. So remember how we talked about using NCDISP to see what the metadata is? All of these are coming in netcdf files. They all have the units provided, and so you can kind of figure out which is which based on the units. And in particular examples, we've already worked them out. So as you're going into the budget, you can start looking at these lists that I have in these slides and in the last set of slides, and just like, where are all those variables? Let me grab all those variables. Let me think about what they add up to. Let me find my domain. Let me find the edges of my domain, and I'd start summing them up, coming through the sides. And you can essentially use the units of these to guide whether is it a salt per unit time coming in? Is it a salt times a volume transport coming in? Is it a salt times a velocity, which then you need to multiply by a cross-sectional area? So you can work your way through those pieces. Does that make sense to everybody? So this is the game that we're starting to learn how to do, to think about how to interpret all these fields that are coming out of the model. And nothing is sort of true or false in this. It's like there are lots of conventions for how you might choose to do it. You might choose to express it as a velocity times a salinity, or a volume flux times a salinity, or salt per unit time. All of those, because we know what the cross-sectional areas are, we know what the other variables are, we can divide them up and make different budgets we want. The only important piece is that all of the information is given to you to close all of those budgets, for freshwater, for salt, for temperature, for momentum. So over time, as we get to know these different variables, you'll start thinking, oh, I could take this one, and that would be my budget to think about. Does that make sense? Okay, so I wanted to talk about one more budget. But before we do that, are there any questions, kind of big picture about this? This is a budget we're going to talk about today, and then also on Thursday, a temperature budget, but for the whole Earth. Yeah.
So on the assignment that we did, we added up the components of all the budgets.
Yeah.
And it wasn't 0.
Yeah.
So is that just an error in the data, or is that supposed to happen?
No. So in that particular case, there are sidewalls and things that were coming in, so it isn't quite closed. We didn't have all the variables together to have it for that particular one. For an open ocean case, those same variables would have added up to 0, where there weren't sidewalls and weren't disappearing parts. And in a different set of the variables, the mass-weighted ones, those also might have been closer to zero because the boxes can stretch and contract. So I guess the point is that there is a fair amount of complexity built into all these stretching of the coordinate systems, and whether it's mass-weighted or whether it's weighted by, so it's velocity times salinity saved as the average of those, or whether they're separately added together and then multiplied by the cross-sectional area, which is what I think we did, which doesn't exactly equal up, because if it's those two are separately time varying, their product is not equal to the combination of two. It's just approximately there. So for this case, I don't expect you to necessarily close it to where it's exactly equal to zero, even though in principle that's true. What I want you to think of is, from a physical perspective, choosing an interesting region, what are the big terms in that budget? Is the most of the water coming in from the side? Is most of the salt coming up from below? Is most of it coming through the sea surface? Those are the kind of questions that are most important physically, because we know that whether or not we can diagnose it ourselves, the model is actually conserving all those things. So it's you're using that understanding that the budget exists to try and explain what's happening. But I don't expect you to actually close the budget all the way to machine precision zero, because we know that the model is doing that separately, and that kind of takes extra fiddling, especially with the expandable boxes. Does that make sense to everybody? So it's to use the concept of a budget to describe a flow scenario.
So it wouldn't necessarily, the total estimated budget wouldn't necessarily, say you do it for temperature,
Yeah.
that wouldn't necessarily say the temperature is increasing in that region.
So it should say whether it's increasing or decreasing, but it's not going to say that it's like exactly equal to zero. There might be like a few percent error. So in that one, I think the imbalance was about 3% of the versus one of the flows. So there was an imbalance of a small amount compared to one of them, and you could spend a lot of time chasing down which one of the variables was the right one to make that imbalance exactly go away. But you discussing which flows are the big flows, and the hot ones coming in and the cold ones going out, and the hot ones are coming in faster than the cold ones are going out, and so the temperature is warming, is an interesting question, even if you aren't closing it all the way to zeroing out all of the budgets. Does that make sense?
Yeah.
And so we could base this on the exact closure of from the model, but that's kind of less interesting because that's not actually the story we want to tell. We believe that the model actually works. The question is how you use thinking about a budget to describe why something is changing in a particular region. Because you're like, look, there's stuff coming and going, and I know the water that's coming in is also going out, but if hotter stuff is coming in and colder stuff is going out, then there's an implied source of heat for that region, and so it must go out through the surface or something like that. So it's putting together connecting those pieces that I think is kind of the most interesting way to go from the budget perspective. Does that kind of make sense? I know that's totally vague. Okay, but this is a good example. This is a good example of one way to think about it. Is a physically important one. On this one, we also cannot close the budget for exactly. We don't know where all the energy in the world goes. We think that a lot of it ends up in the ocean, but when we add up all the bits from the ocean that we measure, there's still more energy going somewhere else that we don't know where it goes. So we take the energy that comes into the planet, the energy that goes out of the planet, we try and figure out what's warming up, what's cooling off, and think about it from the perspective of a budget. So the whole ocean is a big part of the whole Earth's climate system, because the ocean can actually take a lot of energy for a relatively modest change in temperature. It has a very high heat capacity. Okay. What if we consider the whole world ocean as a closed basin? It's kind of like our estuary example. We could think of the inputs and outputs of fresh water and energy. And we can think of the transport estimates within the ocean, like from place to place. So if excess energy is arriving in one part of the ocean and going out in another part of the ocean, something in the ocean had to take the energy from the first site to the second site. And so those kinds of horizontal transfers of energy are essentially the reason why there are currents in the ocean. You get these gradients of stuff, and that ends up sorting itself out into transport from place to place. Okay? So, we talked about this example of an estuary, and we talked about an example of like a model grid cell. This is what we think of when we think of the whole Earth. There's sunlight coming in, about 341 watts per meter squared. There's some of it gets reflected and goes right back out. A lot of it gets reflected off the clouds. Some of it gets reflected off the surface on shiny things in the surface and ice. About 161 watts per meter squared gets absorbed by the surface. That might be the land, that might be the ocean, that might be, depends on where it lands. And then that 161, if it didn't go back out, what would happen? The temperature would have to increase. The amount of energy in whatever surface it's being absorbed into would be increasing. So if it was steady and there was no warming, then this 161 is going to go back out somehow. About 17 of it goes out in hot air rising away from the surface. About 80 goes out of it in evapotranspiration, so basically evaporating water, and then the latent energy in the water going back up. And then some of that comes back down as rain. So it goes up and down and up and down and up and down. But it's still a vertical redistribution between the cloud layer and the surface. And then a huge amount, much bigger than this, goes up in infrared radiation. So we'll talk more about this, I guess, but how many of you know what the Planck black body radiation is? Good, some of you. Okay, so it's like a physics thing, but every hot object emits stuff, and hotter objects emit more stuff, more energy. So the fact that there is a non-zero temperature at the surface means that it emits some radiation. But the clouds are also at a non-zero temperature, so they're emitting radiation back down. And so a lot of this is just cycling up and down between the clouds and then back to the surface. A little bit of it escapes out, and some of it from the atmosphere, instead of being directed down, gets directed up and goes back out. So this equals this minus this if the planet is happy. Okay? So that's the big picture. Oh, I do have a black body radiation. This is showing how much energy in funny units per wavelength. So this is more red over this way, and this is more white, more blue or light. And this is what the sun's emission of energy is, because it's really, really hot. There's a lot of energy at relatively short wavelength. And this is where the Earth's is. So it doesn't emit as much, and it emits it in the infrared because it's cooler than the sun is. If the Earth got really, really hot, it would start to look more like the sun. But this is the thermal radiation emissions from the Earth, the black body radiation. So this part that goes back out is called the albedo, or the fraction of solar radiation that's reflected is called the albedo. So this divided by this. And what would affect the albedo? Color, clouds. So this is what the Earth actually looks like from space. It looks pretty cloudy. So a lot of it's bouncing off the clouds. A lot of it's bouncing off the ice. This one actually doesn't show the ice very well, but the ice, a lot of stuff bounces off the ice, and actually glancing sun off of the ocean bounces off, whereas direct sun will penetrate. You know how like when you look at the ocean and the sun sets over there, it's like really shiny. So the ocean surface depends a lot on the angle of incidence, how much sunlight goes in and how much comes out. Okay? So that's part of the story. And then you can go through really complicated things to say, well, if the temperature warms up, then that emitted outgoing radiation goes up, which then cools because now the energy is escaping. And you can think about these as feedbacks on the system that keeps that budget in check. That's kind of the concept of an energy balance. And they get really elaborate, and some of them have snow and ice and planetary albedo and all kinds of things. So there's a great deal of budget understanding physics stuff that goes into thinking about those energy balances. And in some very basic sense, a climate model is really just an energy balance for the whole system. That's what it does. It keeps track of the incoming energy, the outgoing energy, and where the energy ends up and how it moves around. But let's get to the ocean bit. Sorry, these are a lot of extra slides that we don't need to, that you can take a look at. If we're just thinking about stuff going into the ocean, this is an indication of the average heat flux through the surface of the ocean. It's on order of 100 watts per meter squared, which is about 100 times as big as the global warming signal. So that means that the exchange into and out of the ocean is bigger in the background level than it is in the perturbation due to global warming. But it's obviously not uniform in space. There's a whole lot of energy going into the ocean in the tropics. And then there's a lot of energy coming out of the ocean over big warm currents, like the Gulf Stream and the Kuroshio and also the Arctic. So there's an exchange of energy into and out of the ocean in a very complicated way. And to some extent, it's sort of like the cold water starts to absorb stuff and the warm water loses energy. But it's primarily not because of sensible heat flux, like hot water connecting to cold air and sending it. It's more that hot water is more likely to evaporate, take the evaporative energy with it, the latent heat flux. Okay, so we can figure out how to do this with a lot of complicated things, and we're going to talk next time about how the transport from latitude to latitude drives currents and the winds in the atmosphere. And we could also think about this in terms of not only energy, but also freshwater fluxes. And so there's extra water coming in on the ocean in the tropics and extra water going out in the subtropics. So somehow that water is moving from one place to the other in a current. But getting the budgets of those pieces thoughtfully together is part of the story of what makes the ocean move. Okay? So just like we did with the estuaries, except now we're doing it in big hunks. So which control volume do we need to think about this? Or what's a useful control volume? What are some of the useful ones you might think of?
Ocean volume, but also salt.
Yeah, so we can think of the whole ocean, and we can think of closing the freshwater coming and going, and we can think of the salt in the ocean. They're not really on the global scale any large sources of salt, so the salt might move from place to place, but it doesn't really come in and out. But the freshwater does come in and out in an uneven way from place to place. And the energy comes in and out unevenly from place to place, and so it's got to be rearranged somehow inside the ocean to get from where it's being heated to where it's being cooled. But we also could say, like, what if we just chop off the Pacific? We could think about a freshwater budget for the whole of the Pacific, or a freshwater budget for the whole of the Atlantic, and treat it like an enormous estuary. Or we could take the freshwater budget for the Southern Ocean. And some of those budgets would actually end up being towards the salinifying side, and some would end up being towards the freshening side. So if it was an estuary, what would we expect to be the consequence of that? If we have an estuary that tends towards evaporation dominating, what do we see as a consequence of that? That the outflow was saltier. So if we find an ocean basin that tends to have more evaporation than inflow, we would expect there to be salty currents leaving that ocean, going to other ocean basins. Or if it's an ocean basin where there tends to be an excess of precipitation, we would expect there to be fresher currents leaving that. So in the real world, that's kind of the way it works. Some ocean basins get more evaporation over them, and some get more precipitation over them. And the currents that connect between them carry that characteristic, salinity, being fresher or saltier. And the same is true of energy. Some ocean basins receive an excess of energy through the surface, and some receive a deficit of energy. And so warm currents are flowing from the places that are receiving an excess of energy, and cold currents are flowing from the places that are receiving a deficit of energy. And so those currents are connecting together the pieces and helping these budgets work out so that the ocean is relatively steady in some sense, with all the exceptions of all the there is no such thing as a steady ocean that we talked about at the beginning with the observations, but there is on whole basin scales, the change in the amount of energy is relatively small compared to the inflows and outflows. Everybody's looking at me like that's too much. All right, so we'll come back and talk about this more next time. But the concept of budgets, we can do it in an estuary, we can do it in a grid cell, we can do it for the whole Earth, we can do it for ocean by ocean, we could do it for region by region, we could do it for fluid by fluid, atmosphere, ocean, cryosphere versus the ocean. Budgets are just everywhere in climate modeling, over and over again. So this beam counting of conserving the stuff that's conserved is like the essence of how they work. Cool? All right. Do, do.